Well, last lesson we talked about clouds, and it's real easy to see clouds if we have a robot up in space that can take a picture. And we have two types of satellites that can observe clouds for us. First, the simplest are the visible satellites, which can simply just see the clouds from above. But you can't see clouds if there's no sunlight. So at night, we need to use infrared satellites. The infrared satellites see any heat being emitted or reflected by the clouds. Warm clouds are closer to the ground, so they appear gray. And high clouds are colder, so they appear bright white. It's not as easy to see the texture of the clouds on an infrared as it is on a visible satellite. Now, the orange lines on this diagram are obviously fake, created by a computer. Those are the counties in the state of Pennsylvania and the ones surrounding us. This picture was taken at 10 o'clock. It's snowing, but you can't see the clouds because it's a visible satellite picture, right? In a visible satellite image, you can't see anything at night, so that's a problem. This was the visible satellite picture earlier that day. You can very clearly see the texture of the clouds there, and it's snowing. And one more thing, once that storm passes by, here's the picture the next day. You can see the snow on the ground. Visible satellite pictures can actually see snow. That's how they make snow depth maps.
We got one more problem with visible satellites, besides nighttime, that issue. Here's the deal. Visible satellites, they're detecting how much sunlight is reflected back to them off the clouds. Well, what happens when, say, for example, we got some snow on the ground or a lot of snow on the ground? Here's what the problem is. Snow reflects as much or sometimes more sunlight than clouds do. A big, thick, puffy cloud, well, a lot of snow can reflect just as much sunlight. Case in point, take a look right here on this satellite and radar image loop over 3 hours or so. Look how these clouds are drifting down south as we loop it. There they go, there they go. All of a sudden, whoa, over Lake Erie, look at that. All of a sudden, clouds pop up and they just sit there. While these clouds are moving down and moving south. What's going on? Well, this is partially covered with ice. And after a couple hours, once the satellite got a little higher, we didn't have that issue with nighttime, well, all that ice, it's covered with snow. And that snow is reflecting as much light as these clouds. So the visible satellite doesn't know any better. So it's showing up right there as if it's clouds when it's really snow. So I would see that at the station, and I would take off visible satellite. We usually use a blend between infrared and visible, just because that way we don't have to worry about the nighttime issue. One or the other is going to take care of things. But that is another drawback about visible satellite images. It's really cool when there is snow, you can actually see gaps where there's big bodies of water, like big rivers, so you can tell it that way. But anytime I see something on Doppler radar, or also the satellite image that doesn't move, I go, you know what? That's probably not what it seems. In this case, it most certainly wasn't.
During the day, visible satellites are helpful, but obviously they're not perfect. So here's another visible satellite image. Now we're going to look at the same picture in the infrared. Those colors that you see are created by a computer to help us see where the higher clouds are. The higher clouds are orange, the lower clouds are blue. And typically where you have those orange colors and thicker clouds, you're going to have heavier precipitation. Okay, the higher the cloud, the colder it is, so the brighter it shows up on the infrared satellite images. It's white on the top. Low clouds appear gray. So here are some low clouds on an infrared image at the top of the picture above Michigan and lower Canada, and then down in Texas, that's where you can see the high clouds, which have been colored for us, making it easier to see. Now, our satellites orbit over the same spot of the Earth at all times. In order for that to happen, they have to be about 22,000 miles above the Earth, and they orbit with the Earth. So here's our Earth, and our satellite's going to be about 22,000 miles above it, and as our Earth spins, our satellite moves at the same speed and stays over the same spot. Now, at any given time, we have two geosynchronous satellites watching the Earth. One's called GOES-E for east, and it looks over the eastern part of the United States, and the other is GOES-W, which looks over the Pacific Basin and the western parts of the United States. And you can zoom in very clearly on any spot that you want to see. It has a very high resolution. So we've launched 16 geostationary satellites up to this point. The 15th one is currently GOES-W, the 13th one is GOES-E, and there's GOES-14, which is hanging around in orbit in case 13 or 15 fails, so it's just ready and waiting. We recently launched GOES-R, and it became GOES-16, and that's going to become operational soon. GOES-R can do a lot more things. Every time they add a new weather satellite in space, it can do a lot more data analysis. This can look at space weather, and it can look at storms coming from the sun. It has obviously visual and IR imagery, and it also does some lightning mapping, which is something kind of unique. This is the first picture taken with GOES-16 on January 23rd, 2017. You can see the detail there has a much finer resolution than our previous weather satellites. That's going to give us more data, and that means a better forecast from forecasters like me. These are all the different types of filters that they can use on each one of those pictures. There's tons of them. So I can find specifically where water vapor is in the atmosphere and where it's going. I can key on specific elements. I can key on specific temperatures. It's a very, very valuable tool.
Say you've been observing Earth's weather using GOES satellites for the past 40 years, and suddenly you realize you need to launch another satellite to keep doing it because it's really important. Naturally, you might think to yourself, great, let's just box up parts from the previous satellites, launch them into space, and let them do their thing. Unfortunately, that's just not how it works. Scientists and engineers are always looking for better ways to improve the weather forecast, and for them, images like this from decades-old satellites just aren't quite up to snuff. Thankfully, scientists and engineers have been busy working with meteorologists to improve things, so they have an idea of what data is needed next. That way, when they launch a new satellite, they're adding to what they've learned before, which means even better weather forecasts for the rest of us. So, when you build a satellite in NOAA's new GOES series, called GOES-R, it naturally sets off a flurry of activity. Because they always want to improve things, engineers might change the satellite platform, upgrade all the instruments, and, because it's meant to improve the forecast, add something totally new that's never been done before, like a new lightning mapper. After months of constructive debates, and probably more than a few late nights, they'll finally come to an agreement. Once everything's been approved, the engineers get to design and put the satellite together. However, even though they've built GOES satellites before, it's not just a matter of pulling out the old designs and bolting everything together. Because there's new science to be done, things have to be redesigned, modified, upgraded, built, tested, retested, tested some more, and finally delivered, so that at the end of the day, it all fits neatly atop a giant rocket. Once all that's finished, the satellite launches into space, the scientists and engineers celebrate, and lots of new data starts coming in that improves the weather forecasts for us here on Earth.
So GOES-R is now in space, and by the time you see this, it will be operational, and there's more on the way. You can see about every 6 to 10 years, they launch a new satellite to replace some of the older ones, and once it's in space, it gets a new number. So GOES-R currently is GOES-16. GOES-S, should it be launched, will become GOES-17, and so on. There's plans all the way up to 2036 for weather satellites. And a dumb and useless fact, the first weather satellite we ever launched was back in 1960, the TV and IR observing station, the TIROS satellite. And this was the first television picture it ever sent back to Earth. So satellite technology is improving. That makes weather forecasts better. And really, this has only been happening over the last 60 or so years. So meteorology is a relatively new science, and we're learning all the time, which means forecasting gets better and better. So let's review what we've done this lesson. Higher dew points mean the air has more moisture in it. And as the dew point gets closer to the temperature, the air is more humid. When the dew point equals the temperature, the relative humidity is at 100%. And that creates clouds and eventually rain. We'll look a little more closely at that in future lessons.